When you lift an old appliance off a wooden sideboard and find a cloudy, sticky ring melted into the finish, you are looking at a very specific type of engineering breakdown. The paradox here is that the machine itself worked perfectly. The motor spun, the electronics hummed, and the industrial design was signed off as a total success. The irony is that the only part of the product that physically touches the customer's home is the exact component responsible for permanently damaging it. In standard manufacturing, this creates what we call an unowned problem. A ruined finish on a table or deep dents crushed into a rug never show up in warranty data, return rates, or field failure reports. The company tracks the hardware, but it does not measure the environment around it. Because the primary function of the machine never failed, the internal spreadsheets reflect a flawless 100% success rate. The damage exists entirely outside the manufacturer's field of vision. That leaves the consumer to independently bear the cost of repairing an invisible corporate blind spot. To see how this happens, we have to look at the timeline of product development. The industrial design gets locked in early, and weeks later, an engineer picks a set of protective feet from a supplier catalog in a single afternoon. That late-stage catalog choice introduces two distinct modes of failure. The first is chemical. Manufacturers add compounds called plasticizers to make rubber or vinyl feet flexible. This diagram shows the long-term chemical reaction. Those plasticizers do not stay put. Over months and years, they leach out of the rubber and migrate directly into whatever the foot is resting on, softening and discoloring the lacquer finish below. The second mode of failure relies entirely on mechanical forces and basic arithmetic. This graphic maps contact pressure, which calculates total mass by dividing it into the available contact area. Place a heavy object on 4 tiny, hard feet, and those points drive their entire weight into a few square millimeters. The math guarantees a deep indentation in the flooring beneath it. Chemical rot and mechanical crushing both result from relying on a tiny, afterthought component to manage the physical load of an entire product. Throw a motor into the mix and you get a third problem: dynamic vibration. Most household floors are imperfect planes. When a 4-point object sits on an uneven surface, one foot usually isn't carrying its share of the weight, causing the whole machine to rock aggressively across a diagonal axis. When a washing machine starts walking across a laundry room, people instinctively buy aftermarket anti-vibration pads to stop it. They pay out of pocket to correct a design decision. The engineers who selected that late-stage foot are trapped by conflicting requirements. The material needs to grip the floor tightly so the product doesn't slide, but it also has to leave the surface perfectly unmarked. Rubber grips effectively, but guarantees chemical surface damage. Felt spreads the weight and protects the wood, but slides easily under a heavy load. Asking a single piece of material chosen in the final hour to solve both friction and surface protection is a structural contradiction. It guarantees failure in one direction or the other. To solve this, we have to look past the supplier catalog and return to the foundational physics of the product. You cannot fix the physical reality of a heavy, vibrating object resting on 4 small points by changing the rubber compound. The material was never the true variable. The true variables for pressure and stability are total mass, number of contact points, their area, and center of gravity. This determines the overturning moment. A tall, narrow structure inherently rocks more than a low, wide one. No foot material compensates for unstable architecture. These are strictly architectural variables, locked in during the very first weeks of concept design, months before an engineer ever opens a parts catalog. The actual solutions require structural choices: adding more feet, expanding the surface area, designing a compliant layer, or lowering the center of mass. Here is the economic reality of product development. Making these structural changes costs next to nothing during the concept sketching stage, but it becomes prohibitively expensive to alter once manufacturing tooling has begun. By using tools like Depix Design Intelligence, teams visualize and resolve these physical contradictions early in the process. It proves a hard rule of manufacturing: design decisions are as cheap as a sketch, but brutal once they are tooled.